And they are able to do this by something called interstellar dust. Interstellar dust are tiny particles. They're mostly made of silicon or carbon, and the really important part here is that they're almost always covered in ice. And this makes it so that they can easily travel, or they can easily make water go around. And also is really just important to the idea of, it's just really important in the universe. And in new research, they found that comparing two pieces of data on the same supernovae region, they realized that in 2008 there was some dust in that region. And then when they revisit it with a different telescope, the James Webb Space Telescope, at the same exact location, in 2023, they found that actually the dust was not only continuously being produced, but it was being produced at a higher rate than it was when it was originally discovered. And so this is really significant because it's proving that in the same region of what happens after the supernovae, there is not only water being formed, but there's also this continuous production of the dust that carries the water that is able to do so over time. And although these may seem like really small findings, basically anything in learning about the early universe is a pretty big deal. It's really far away, and we have no ability to have a direct observation because of something called cosmological redshift. And although it sounds really dramatic, it's simply the fact that our universe is expanding, and as it does, everything seems like it's further and further away. And so, because of that, we don't yet have the technology that we can see any of these things, so it's really hard to find stuff or find data that can prove anything. So often, kind of findings like these are really reliant on creative solutions like computer modeling. And lastly, the future and importance of studying the early universe. That being said, there are really exciting things on the horizon for studying the early universe. Pictured here, we have the James Webb Space Telescope, which could soon give us a glimpse into population 3 stars and early stars and the remnants left behind by their supernovae. Also, it really pushes our human knowledge to the best possible way and our astronomical technology. Practically speaking, studying water formation in the early universe will help with future habitability research and finding more habitable planets. But I think more importantly, it helps us better understand the timeline of our universe. As Dr. Nielsen said in her Crump lecture, there's something beautiful about pursuing science for science, and even though we shouldn't be able to see or understand anything about our universe, we are still trying to do so every day and building our technology to be able to do so one day. Therefore, these findings about early supernovae production of water and dust help us to better understand the world and our universe around us. And with that, thank you for listening.
Okay, we have some time for questions. Anyone have questions for us?
So I was just wondering, if the dust was able to spread across the whole universe, is there a reason why Earth's concentration of water was much more concentrated and why there's not other planets with more water?
Well, I think it's more about how dust also can make up planets and makes up a lot of planetary objects in the universe. So I think it's just that perhaps the dust that forms our planet had more ice covering it, and that there was more of that in the founding of our planet. Sorry. Yeah.
Were they able to find more habitable planets? Like, were they able to find any of the water on any other planets? Would you know?
Yes, they have found water on other planets, especially in the form of ice is really popular. So they have been able to do that on other icy exoplanets especially.
how do the scientists know that those computer models are accurate if it's not something that you can like observe?
So that's the real issue with studying this is, again, we can't observe it, so there's a lot of variables that we don't know. But really, they try to factor in as much as possible, so they really have the kind of chemistry aspect of it. We know a lot of things by observing modern supernovae that we can observe and that are significantly closer to us. So applying kind of our knowledge of that to the simulation, and then also what we know about the early universe and the gases that made it up, they're both really quite accurate, but again, we're never quite sure in that. Thank you.
How is the dust produced at a higher rate, significantly after the supernova already exploded?
I'm not entirely sure. I think that is part of the kind of continuing research on it. I think it was really hard data to achieve, but I think finding that there was more dust was just really significant in the first place. But I think some of it could be a collection of it happening, but also it's really hot still, even fairly long after. So as it cools, it's probably more likely to compound and become dust.
This might be a very detailed question, but you talked about cosmological redshifting, and I'm just wondering if you could expand on that and how does that relate to the expanding of the universe?
Yes. Okay. So it does relate to the expanding of the universe, and so it's in terms of redshift. It's usually as something gets further away from you, it's more redshifted. It's more, I guess, theoretical in that sense. Is something's not moving away from you, but rather because everything is expanding at the same time in the universe, it seems as though it is, and therefore it is just made further by that, if that makes any sense.
First of all, I just want to thank everyone for coming out here. It's truly an honor to speak in front of you about something that I'm truly interested in. In tonight's presentation, The Sun in Our Hands, will focus on how breakthroughs in streamlining the efficiency of nuclear fusion technology can put an end to the energy crisis and bring a new era of innovation. Here's the thing. Our planet is on a crash collision course towards a seemingly irreversible threat. This past year, global temperatures exceeded 1.5 degrees Celsius above pre-industrial temperatures for the first time. Why is this significant? Well, in 2015, at the Paris Climate Agreement, two thresholds were introduced. One, a 1.5 degrees Celsius threshold that we were to stay under to lessen the effects of climate change. And the second, a 2 degrees Celsius threshold that we were to, at any cost, not go over, because the effects would be disastrous and very hard to reverse. And while renewable energy sources exist that are pushing the deadline back, we're actually on course to reach this 2-degree threshold by the late 2040s to early 2050s, which is less time than we think. Our dependence on fossil fuels is only increasing, and our time is running out to find a solution. Although, the solution may actually be hidden in the night sky. Every star in the universe is powered by something called nuclear fusion. What is nuclear fusion? Well, to put it simply, nuclear fusion is the process of smashing the nuclei, the center of atoms together, of light mass to form a single, heavier one, producing an incredibly high amount of energy in the process. Although, fusion is much easier said than done because of a little thing called atomic repulsion. Atomic repulsion is basically when the nuclei of atoms are positively charged. Because things of identical charges really don't like being near each other, it creates an electrostatic repulsion between them. This, in most situations, is very good. Without it, atoms would simply collapse in on each other and the universe would lack any structure at all. Although, what if we were crazy enough to break past this atomic repulsion? Well, we would need a combination of extreme temperatures and pressures to break past it. This is a reason why fusion requires so much energy, because it also has to break past this atomic repulsion layer. But it's also why stars are so good at fusion. The sun's combination of its extreme gravitational pressures, extreme temperatures, and abundance of fuel trapped inside of the star fosters the perfect environment for nuclear fusion to exist, because it can simply blow right past the atomic repulsion layer. However, the secret of nuclear fusion is not kept just for the stars. In fact, we've known how to harness the energy of nuclear fusion since the dawn of the Cold War. One of the first applications of nuclear fusion technology actually came in the form of weapons. On the left, you can see the little boy. This was the bomb that was dropped on Hiroshima in World War II. It had an explosive yieldage of 5 kilotons of TNT. That's 5,000 tons of TNT. This was a fission bomb, not to be confused with another member of its nuclear family, fusion. Fission is the splitting of atoms, which releases energy, while fusion is the combining of atoms, or the nuclei of atoms, sorry. On the right, you can see the star bomba. This is the most destructive and powerful bomb ever detonated on Earth. It had an explosive yieldage of 50 megatons of TNT. That's just about 10,000 times more powerful than the little boy. And it achieved this because it is a thermonuclear bomb, or a fusion bomb. Those terms are somewhat interchangeable. And this goes to show the real difference in power and the potential of power that exists within fusion. At the moment, all current nuclear reactors are powered by a process called fission, which we touched on earlier. When you think of a nuclear reactor, fission is likely what's backing it. While nuclear fission is great, it actually has a lot of problems. Nuclear fission produces a monumental amount of radioactive waste, which actually stays dangerous for thousands to even millions of years. And it's actually becoming less cost efficient as opposed to other means of energy production, such as burning fossil fuels. Although, nuclear fusion is actually considered better than fission, and really the epitome of energy production means in general, because it has virtually zero radioactive waste, and really very little waste at all, has a virtually limitless fuel source, being hydrogen isotopes. Hydrogen is the most abundant element in the universe. 75% of the universe is made out of it. So if we had to pick anything to be a fuel for energy, it would be hydrogen. And last but not least, it has a higher energy yield per unit of mass of fuel than not only fission, but just about every other means of energy production that we know of. It has 4 times more power per kilogram of fuel than fission, and almost 4 million times more power per kilogram of fuel than burning oil or coal. This is where the brilliance of nuclear fusion sets in, and why it's so powerful that we must create it on our own. Because fusion could effectively provide limitless energy because of that limitless fuel source and higher energy yield. So how can we actually create these artificial stars on Earth if we don't have access to the same gravity of the sun? Well, we must compensate with temperatures that actually exceed that of the sun's by just under 10 times to overcome atomic repulsion on our own. Historically, there are 2 ways to achieve fusion on Earth: inertial confinement and magnetic confinement. And let's go into what those actually mean. Inertial confinement achieves fusion by rapidly compressing and raising the temperature of a medium of fusion fuel. The rapid compression of this fuel, combined with the extreme temperatures, allows the nuclei of these atoms to fuse, releasing energy. Imagine holding a water balloon in your hand and squeezing it until it can compress no longer. It would then release, upon popping, a burst of energy that would be extremely hard to actually gather any energy from. Similarly, inertial confinement produces a very chaotic burst of energy that is hard to control, which is why it's used in things like bombs and not in commercial fusion reactors. Although what is used in nuclear reactors is magnetic confinement. Magnetic confinement employs an array of super powerful magnets that surround a donut-shaped ring of deuterium and tritium, isotopes of hydrogen that are the preferred fuel for fusion. This deuterium and tritium is superheated to become plasma. And this is an important step, because when deuterium and tritium reach temperatures high enough to become plasma, they actually lose their neutrons. Their neutrons fly off. And remember that, because it will become relevant later on. Because they lose their neutrons, it leaves behind only a positive charge, allowing it to be manipulated by a magnetic field. And that allows us to actually be able to control the plasma in a very controlled way, which is why it's used in nuclear reactors instead of things like bombs. Okay, well, now you may be wondering, if we know how to create nuclear fusion reactors, then why don't I hear about anything about them producing any energy for the grid? Well, it's because fusion is so insanely difficult to do. The plasma within a reactor is actually hot enough to vaporize any material in the universe that it comes in contact with. And it requires a huge amount of energy to actually even sustain a fusion reaction. Because of this, fusion has perpetually been said in the science community to be less than 30 years away for the past 60 plus years. It seems like a never-ending cycle. Although to combat the extreme temperatures of the plasma, we employ magnetic confinement, which we touched on earlier. Magnetic confinement is used because it allows for the containment of extremely hot charged plasma without actually touching the walls of the reactor vessel, which would cool it down. The walls of the reactor vessel would take away energy from the plasma, cooling it down and preventing fusion from occurring. And not only that, it would contaminate the plasma of deuterium and tritium with the sheared off particles from the wall, which we don't want. Although, while scientists have taken leaps and bounds in improving the technology of nuclear fusion, one problem still remains triumphant: the inefficiency of it all. Because the action of fusing the nuclei of atoms requires so much initial energy investment, ever yielding any more energy than was actually put in is extremely difficult. On top of the atomic repulsion adding to this high energy investment, it is also impossible to guarantee a fusion reaction. What do I mean by that? Well, fusion is actually exceptionally rare. To combat this, we have to increase the amount of plasma or fuel volume that we do. When we do this, we have more nuclei that are actually available to fuse, and thus a higher probability that a fusion reaction will occur. That's also an important thing that we must remember earlier on. Because we have to increase that volume of plasma, and because fusion is actually much rarer than we think, we're actually heating a lot of that plasma to actually do nothing. A lot of that energy that we put in is being wasted. So on top of the atomic repulsion, that is also another layer that adds to the inefficiency of nuclear fusion, which is the major limitation of why it's not economic to do so on a commercial level. And it's why we don't have any commercial fusion reactors on the grid. Although, in 2022, the tide finally turned. The team at the Lawrence Livermore National Laboratory in California, or LLNL, successfully sustained a net positive energy output from a fusion reaction for the very first time in a revolutionary process called fusion ignition. Fusion ignition is simply the action of getting more energy out than was put in. So how did they do it? How did they do what hundreds, thousands of scientists couldn't do before them? Lasers. Specifically, 192 of them. The lasers, they employed an array of extremely highly powerful lasers focused towards a small, pill-sized and shaped core of deuterium and tritium fuel. The LL&L team exceeded the pressures and temperatures of the core of stars by rapidly compressing the core with the extreme heat provided by the lasers. When you have the extreme heat, the pressure increases. And when the pressure increases, it compresses. And now you have the three keys for fusion: compression, temperature, and fuel. But that's been done before. What makes this so special? How did they achieve net positive output? Well, they actually focused, instead of maximizing the energy output, they actually focused on minimizing the energy input. The lasers that they used are extremely energy efficient. And they actually didn't use a lot of fuel to do this, which also minimized the amount of energy that they had to put in. Because of this, they actually were able to get more energy out than they put in. This is a revolutionary achievement in scientific history. Although it's important to note that it exists more of a proof of concept than something that could ever produce energy for the grid. It's simply too difficult to get enough energy out of this to put anything onto the grid. Although, perhaps the most promising nuclear fusion project ever is the International Thermonuclear Experimental Reactor, or simply ITER. ITER is an international collaboration between dozens of countries pulling together their efforts to create the most advanced dry run of a nuclear reactor ever, paving the way for fusion to exist on a commercial level. So how does ITER differ from others? Well, then, rather than using the laser-driven implosion design that is seen from the LL&L team, they actually use the tokamak design that has been around since virtually the conception of nuclear fusion technology. If we look back at tokamaks in the past, we see something very interesting. The man right there is just about the height of that reactor, and that reactor fits well inside the room he is standing in. If we take a look back at ITER, we can see what makes it so starkly different. ITER is almost 4 stories tall. The difference in volume between a room and a building is significant. That volume goes towards the plasma. And if you remember earlier, more plasma equals more fusion reactions. Because of this, ITER is able to produce much more fusion reactions than any other fusion reactor ever, because it's simply the biggest ever. This is why it's so revolutionary. Although, with anything, there come significant challenges. While these are only 2 of the significant challenges that ITER faces, I believe that these are the most major. Firstly, tritium. Tritium is one of the 2 fuels for fusion and is a hydrogen isotope. Although despite being a hydrogen isotope, it is virtually non-existent naturally because its half-life is only 12 years. A half-life is basically how long a material has before it becomes unusable in this case. However, to combat this, ITER actually does something very special and very cool. They actually make their own. They use something called a tritium breeder, which is very complicated, but I'm going to explain it in 3 steps. Firstly is fusion. You actually need a fusion reaction, first of all, to get this process going. Because if you remember, the neutrons that were flying off of that plasma, that gave the plasma that positive charge, actually have a use now. They actually travel through the walls of the reactor and hit a layer of beryllium. This is the second step. Beryllium is something called a neutron multiplier, which is exactly what it sounds. As a neutron hits it, it multiplies and amplifies the amount of neutrons that are coming out of it. And this leads into the third step, the actual tritium breeder. The tritium breeder is a layer of lithium that exists also within the reactor wall, that when neutrons hit it, it splits into many different products, one of which being tritium, which is that fuel for fusion. ITER simultaneously uses and breathes enough tritium to sustain its fusion reactions. And then secondly, another major problem that it faces also has to do with the walls of the reactor. Well, since it uses magnetic confinement, the plasma in the walls of the reactor are not directly touching. It still has to do a lot because of the corrosive particles that are shearing away from this plasma and the temperatures that are making its way to the wall. To combat this, ITER uses tungsten, one of the densest and most resilient metals in the universe, as its first wall, which is the wall that surrounds that is inside the nuclear reactor, that is the first point of contact, or like the closest point of contact between the plasma. Tungsten is used in a lot of nuclear fusion reactors. This part is not what makes it super special. What makes it super special is that they use a boron powder coating. What this means is that as the reactor is running, they sprinkle in boron powder, which pretty much acts as a shield, a temporary, disposable, and cheap shield to go on top of the tungsten walls. This significantly prolongs the tungsten wall's lifespan because those corrosive particles end up hitting the boron instead of the tungsten, significantly prolonging the tungsten wall's lifespan, which without the boron would only have a shelf life of 12 years, which would dramatically raise the cost of the wall and the fusion reactor as a whole. These are just two of the many challenges that ITER is innovative to solve. So, when can we expect commercial energy? Well, it's complicated, but as of now, ITER plans to achieve first plasma, meaning a sustained nuclear reaction, in come 2035. While ITER will not actually generate any power for the grid, it will provide the necessary research needed for commercial power plants to exist in the coming future. I think this is as good a time of any to mention that there are many different projects that I simply couldn't have highlighted in this presentation that are just as promising for nuclear fusion as ITER and LLNL. And I would be happy to go further into any of that if you're curious in the question section. A new era of innovation is hurtling across the horizon, and it's drawing closer by the second. With the effectively limitless supply of energy, of clean energy that nuclear fusion can generate, the ceiling that our currently limited supply of energy production supports will disappear into the stars, the same stars that inspired us to make our own here on Earth. With fusion, we can simply filter the salt water from the ocean and make clean drinking water using a notoriously energy inefficient process of desalination. Similarly, we can just suck the CO2 that is plaguing our atmosphere clean out of the air with the process of, with those things that you see at the top right. The applications are endless, but the solution is singular. I'm truly optimistic that we're closer to nuclear fusion than we've ever been. And once it finally arrives, I promise that the world will never look back. Thank you so much for your time.
Hi. So I know for a lot of renewable sources, a big problem is budgeting, and like in the short term, it's a lot of money, even though there's going to be a lot of benefits in the long term. I'm just wondering, have you seen that for any of these methods?
Yeah. So at the moment, nuclear fusion reactors are extremely, extremely expensive. This is a big problem as to why there's not a lot of research going into them in the first place. Part of that has to do with the inefficiency of it all. It has to do with actually most of it. But this is a renewable energy source that once we actually figure out, it could provide, in a sense, infinite energy, which once we have that reactor, just give it some time and it will eventually outweigh the costs. So I think that once this will be the epitome of a clean energy source in the future. Yeah, question.
I'm curious if there's an effort to by these companies to patent some of these technologies, or are scientists willing to collaborate together in the interest of the planet?
Yeah, so it's actually ITER is actually a very unique like situation. Many different countries are like building and designing many different types of components that go into ITER. We can actually see this right here. Like there's many different there's many different countries contributing to the project, and many of these countries don't get along with each other politically, but they're all combining their efforts to, get to that end goal, right? And all the scientists that are working on this project also recognize the significance of nuclear fusion technology and what it could mean in the future, which is why these scientists have probably convinced their countries that this is necessary. And really, we've tried doing it alone, but having the help of others in science is, the most powerful thing. So, yeah.
I'm wondering, what kind of, dent, they make a lot of energy and they, take a lot of energy. So what kind of, dent does the consumption, take from the, production of the generation?
So right now, the debt is immense because you're putting in more than you're getting out. It's simply not economic. What ITER is all about is pushing that past and getting that efficiency to go up, to push the output to outweigh the input. So right now, nuclear fusion is just about the most inefficient way to create energy on Earth. But that will change, hopefully, in the soon future.
My question is about safety, because I feel like a lot of times when we talk about nuclear reactors, the possible damage to the surrounding area or to the people working in those conditions is a factor that's talked about. So I was curious to hear your thoughts on that.
Yeah, so the thing that's really special about nuclear fusion is that it can't actually yield a meltdown like a nuclear fission reactor can. And as I mentioned earlier, it doesn't produce any radioactive waste. It's just this is why I called it the epitome of energy production, because it has, in theory, virtually zero negative side effects besides getting the materials and mining them to create the fusion reactor itself. So it has no immediate negative effects. Yeah.
You talked about how an advantage of the laser being its efficiency in minimizing the input, but then you also talk about how the powerfulness of ITER lies in the large amount of plasma as a fuel, so which seems kind of contradicting. So can you explain the relationship between the input and the output a little bit more?
Yeah, so the ways that ITER and the LNL, laser-driven implosion design works, they're fundamentally different. They both eventually reach that plasma condition, but this, in the real world, if you look at that, there's some measurements next to it. It's only just over a centimeter big. That's not a lot of thing that you have to actually heat up to that temperature. That's why the input is so much less. Even if you had if you scaled everything up, if you had thousands more lasers, because you're scaling that core up, it's just harder to heat up. But when it's in a magnetic confinement, tokamak, we actually haven't created a greater output than input in a tokamak reactor yet. But that will hopefully come with ITER. And yeah, does that answer your question?
Okay, let's thank Bill again because we can do some more, but thank you.
Okay. Thank you, everyone, for being here. So I'm going to be talking about outwitting an ingenious worm, beating schistosomiasis with nature's help. So what is schistosomiasis? Schistosomiasis is a parasitical waterborne disease. That means it goes through a parasite, a worm, and it happens in bodies of water. In this case, it's mainly happening in fresh water. So right now, it typically is happening in tropical or subtropical areas, and more specifically in poor and rural communities. So why should we care about schistosomiasis? Well, this past year, I had the chance to meet a 16-year-old girl. She's about the same age as a lot of us in this room, except she is one of 300 million people worldwide infected with schistosomiasis. So some of her current symptoms are blood in her urine and her feces, and chronic fatigue. And something that I learned is that she actually turned down temporary treatment for schistosomiasis. So some of the long-term symptoms that she could experience are damage to her spleen, her intestines, her lungs and bladder, infertility, and unfortunately, this is a tiny part of the list of the long-term symptoms that schistosomiasis can cause. So if she does not get treatment, schistosomiasis can eventually be fatal. So let's meet our enemy here. It's called the schistosoma worm. So it starts off as something called cercariae. So the cercariae live in the water, and something that's really important to how this disease spreads so fast and so much is that we have multiple different hosts. So we have something that's called an intermediate host. So snails in the fresh water, they get the disease and they spread it. They just cause even more problems. And then we have our definitive host, which is humans. So cercariae penetrate the skin of humans. They release what's called schistosomia. And schistosomia, basically, they travel through the human body. So they start off in the lungs. They cause a bunch of problems in the lungs. And as they're making their way through the body, they form into adults. So a schistosoma worm kind of comes in a pair. There's a male and a female, and that's kind of the final form. In our snails, there's a similar process. It's a little bit different, but the end result is the same. You get a snail that's infected, and they spread it to other snails. They spread it in the water. So how does the disease spread? So first of all, infected people release larvae into fresh water. A huge problem with this disease is that fresh water in these communities that it's really prevalent, a lot of the times there's only one freshwater source. So everybody's using it. So larvae infect the freshwater snails and they multiply inside them. The disease gets spread into the water by snails and humans at the same time. Through the snails, new larvae are released into the freshwater. People use the freshwater for bathing, drinking, for their jobs. It's really like a huge part of a lot of people's lives. And so by being in the water, you're susceptible to the disease. So the worm penetrates the human skin and they release the larvae, and worms grow and they lay eggs inside the body. And so it's kind of an endless cycle there. So there are temporary solutions to schistosomiasis, but they're not that great. First, we have chemical molluscicides. So they do kill the snail hosts. What happens is they're chemicals that are put into the fresh water. They kill the snail host, but the problem is they are strong chemicals and they do hurt the ecosystem. They can damage other animals, they can pollute the water, and they can also even hurt humans sometimes. And then second, we have praziquantel. That is a medicine. So it's easily taken, it's an oral pill, but the problem is that it's not preventative in any way. So if someone had schistosomiasis, they took praziquantel, and they were cured, the next day they could go into the water and get it all over again. So it's not really that effective. It also needs mass administration to make a huge difference. So everybody needs to take it. And something that I saw a lot is that there are a lot of different reasons why it's not that easy to get praziquantel. So in 2021, a Stanford team came up with a brilliant plan. They figured out the answer to this is shrimp. they decided to deploy prawns into infested waters in order to reduce disease. So why shrimp? Why does shrimp work? So they figured out that prawns eat the disease. They eat the disease-spreading snails, which eliminates a huge factor of the spreading of the disease. Unlike the chemicals, shrimp are eco-friendly, and if anything, they can actually boost the ecosystem. And an added benefit that they found out is that shrimp actually boosted local economies, because it provides a new industry, it provides jobs, and it provides food. So they decided to put this to test. There was a case study done on the Senegal River. So a little bit of background. On the Senegal River, some dams were built in order to boost the agriculture. What ended up happening is that ended up causing overpopulation in the disease-carrying snails. So schistosomiasis went way up. So they decided to deploy prawns into one water source, which is supplying a lot of different villages, a huge area. And they found out that introducing the shrimp led to a dramatic drop in disease rates in the villages using that source of water. After they added the shrimp, there were fewer snails, which means there were fewer worms, and just in general, less disease. They also found out that it helped to restore the aquatic ecosystem. So again, there was kind of an imbalance because of the overpopulation of the snail host. So adding the shrimp, which are a predator of the snail host, kind of restore that balance. So it's a good plan, it's a good solution, but it does require a lot of things. First, there has to be a balance against overfished shrimp. So if shrimp is going to be used as also like a boost for the economy, people are going to be fishing it, people are going to be hunting it. So if people do that too much, they can get it to the point where the snail population can actually explode again. And all that would do is just bring back everybody's problems. Second, communities have to be made aware and in full support. And a huge reason why schistosomiasis is so prevalent is because there are many different factors that go into it. It's a complicated disease, and it's a persistent worm. And then lastly, there needs to be a multi-strategy approach. There has to be access to safe water. So for example, if there's a infected water source, it would be great if people could get access to a clean water source so that they didn't have to risk reinfecting themselves. Unfortunately, because of the location of a lot of these communities that are affected, it's hard to get access to safe water. Second, medication needs to be taken. The shrimp are great, but they don't actually kill the disease once it's in the human body, so praziquantel has to be taken to do that. And again, awareness is a huge part of schistosomiasis, so there needs to be public health education. So I want to zoom out a little bit because I want to emphasize that schistosomiasis is not something that's just happening in one specific location. It's global. Again, 300 million people, and on this map you can kind of see it's on every side of the globe. Something that's interesting is that there are actually different types of schistosoma worms. For example, in the South America and the Caribbean, there's the subspecies S. mansonia. And so each subspecies has its own little traits, but they're all mainly the same. I just think that's a huge example of how important it is to raise awareness, because I think it's pretty incredible that seafood can solve such a huge problem. And so imagine if we apply that to other things. And so in conclusion, it's a tough disease, but we have the answers. We can outsmart the worm, and I think schistosomiasis is an example of how important creativity is to STEM and to science. And last but not least, we can't forget about our hero, the shrimp. Thank you.
I have a question. You said the snails breed the worm. The worm grows inside the snails, right? So if the shrimp eats the snail, and then the people eat the shrimp, don't they just eat the worm?
Like this, the parasite is not, like, I guess, successful in shrimp, so that's not really a problem. That would be really bad if it was. But yeah.
Okay, what makes it so unsuccessful in shrimp? Do you know?
Not really. I
Okay.
think they just figured it out. It's a happy coincidence that shrimp is a predator for the snail host. But I mean, it's a complicated disease. Even the fact that there are different traits for different subspecies of the worm just goes to show how like nuanced it is.
Why did the girl that you met choose not to take the medication?
Yeah, well, I talked to her for a bit, and we convinced her in the end. She said she was gonna. I don't know if she's actually going to, but she said she didn't like the taste. And unfortunately, that is actually a much bigger problem than you'd think. It's hard. Children are infected just as much as adults. It's hard getting children to take a medicine that tastes awful. And as like trivial as it sounds, it's actually a huge part of the reason why the medication by itself isn't a good enough solution.
Are there any concerns with like releasing the shrimp into the ecosystem? Are they like eating anything else, or is there any concern that they might disrupt the food chain in like any other way by their presence?
Yeah, so a concern was that like shrimp are not always native to the area that they might be introducing. So it depends per region. For example, in Senegal, shrimp were native. So what they were really doing is reintroducing it, like making sure, like just kind of giving it a boost. They weren't completely adding a new factor, but there's still questions in the air about like the effect of adding shrimp as a new factor to an ecosystem. It would definitely create a change, but so far they haven't found anything that's huge, anything that creates a problem. So.
Is there like any specific way that they can get so many shrimp and then release it into many different bodies of water?
I haven't really thought about that. Scientists are smart. Yeah. Sorry. Definitely. So water, that's another part of like why there needs to be, like it needs to be multifaceted. Yes, so the water itself can be infected, but not all the larvae are disease carrying. But yeah, that's why sanitation is a huge part of it. Getting access to like clean systems of water would hugely change the infection rate.
Are there any similarities between the places that are that have the disease, the map that you showed? Are there any Are there any similarities between those locations where the disease is prevalent?
Yeah, so they're all tropical or subtropical areas, and so there are differences. There are slight differences, but they all kind of have similar like climates and just like behaviors. So there are differences in the different regions, of course, which is why there are different types of the worm, because the worm adapted to that region. But yeah, there's a similarity between them. They're all subtropical or tropical.
Do you know? Do you know if there's been any research done on how to prevent the like growing population of snails because of the construction of dams? Like, is there any way to have the construction of dams not affect or have the construction of dams like have the snail population like grow and negatively affect the people there?
Yeah, for sure. That's definitely a part, like a huge factor. Oh, forgot your question. Can you say it again?
mentioned that the dams, like the construction of dams made the snails grow, like the population grow. And I was just wondering if there's been any like research done or if there's any way to prevent the growth of snails with still building dams.
Yeah,
Because
and I mean, I honestly think it becomes a thing where it's like the risk is not, the reward outweighs the risk. Schistosomiasis is such a big thing that like, if you live in one of those areas, you're probably gonna have it in your life. So I think the way that it's not necessarily the top priority, but yeah, like that is a huge problem. That's what makes the disease spread so far. But I think the focus is mostly on the disease itself.
Hello? Oh, yeah. So you said that the worms can adapt to different environments. Is there a chance that it could adapt to environments here?
Oh yeah, it's like it would be hard, but definitely. But there are also a bunch of different factors, like the fact that we're more developed, that makes it harder for the disease to have such a devastating effect. That's one of the factors. It's unlikely that's gonna happen just because it's so complicated here, but for sure it's possible.
Sorry. I was just wondering, like, what is the effectiveness of one shrimp? Like, how many snails can one shrimp eat? That makes sense. Like, what is the effectiveness of one shrimp in comparison to eating snails?
You know, that's a really intellectual and deep question that I'm gonna have to think about it later, because honestly I have no idea, but I hope they eat as many as possible.
All right. 1, 2, mic check. All right. Hi, everyone. My name is Kevin, and it is my honor tonight to be here to present you with my project, which is on the rapid testing of antibiotics employing droplet microfluidic chips. Now, I hope you guys remember, but a couple of months before spring break, our campus was attacked by a series of diseases. According to the words on the street, there were up to 6 different kinds of diseases happening simultaneously. But the most influential one was none other but the type A flu. Now, the flu is generally caused by influenza viruses, and even though it is highly contagious, as most of us have experienced, it usually comes with a low mortality rate, especially to patients who are vaccinated. But most of the times, the flu has uninvited friends, and that is bacterial infection. Usually, bacterial infection happens simultaneously with the flu, because when a patient is infected with the flu, their immune system is working 24 hours straight, and it's working at a high intensity. This makes the patient's body more fatigued and more susceptible to other types of infections, such as the bacterial infection. Now, you may have recalled, when you had the flu, the pain that comes from the throat whenever you swallow is a type of bacterial infection. And when the patients start to recover, they tend to also develop other kinds of bacterial infection like pneumonia, which is a bacteria that targets the lungs. Now, this is a very serious problem because not only does it put the patients at a greater risk, but it also prolongs the medical process of the patients. And in order for us to combat bacterial infection, we need antibiotics. Now, just a quick basis on antibiotics. There are mainly 2 types of them. The first one is narrow spectrum antibiotic, which is represented by the green pill. Now, as you can see in the cage that the pill is holding, we have the same color of angry birds. Now, that means that the narrow spectrum antibiotic targets a specific kind of bacteria. The second type, which is the broad spectrum antibiotic, is quite the opposite because it targets a variety of bacteria. But beware, this versatility comes with a price. Because it targets a lot of bacteria simultaneously, it is more likely to cause bacterial antibiotic resistance within the patient. Now, this is because the broad spectrum antibiotic is much more powerful than the narrow spectrum one, as it targets more bacteria at once. Once it enters the patient's body, it will kill both the sensitive bacteria and also the normal bacterial flora that resides in your body originally. Now, this causes what we know as dysbiosis, which refers to the imbalance between bacteria in human bodies. And this imbalance would, and due to this lack of competition of other bacteria, the resistant bacteria that survive after the first round of purge would develop freely at a much faster speed. Now, this causes the development of the antibiotic-resistant bacteria that is basically, as you may see from like some sci-fi fictions or movies, what we know as supercells that is basically invisible and cannot be killed by any type of antibiotic. Well, obviously, that's very hard to accomplish in reality, but there's this potential. And you may wonder, since the narrow spectrum antibiotic is much safer than the broad spectrum one, why don't the doctor just prescribe the patients with the narrow spectrum antibiotic from the beginning? Well, it is not as simple. Because current bacterial diagnosis time that is conducted in most hospitals take a few days to accomplish. So for doctors, before they can obtain a result of which type of bacteria the patients are infected with, they're not able to prescribe with narrow spectrum antibiotic because they don't know which type is useful. Therefore, they're forced to prescribe with the broad spectrum antibiotic, making broad spectrum antibiotics the more empirical use, both in terms of treating patients and also clinical studies. Now, the abuse of such broad spectrum antibiotics naturally leads to the more likelihood of creating antibiotic-resistant bacteria. And here's just a quick graph to demonstrate the current diagnosis method applied in most hospitals. As you can see, there are several steps. So the doctors first have to collect clinical samples from the patients, mainly in terms of blood or urine samples, and then they will put them in culture overnight in Petri dishes, and then they will incubate for about 46 hours, and they will put it in the AST machine. AST stands for the antibiotic susceptibility testing. And all of these steps, when you add them together, the minimum time it takes for the process to yield a result will be at least 1 to 2 days. And with that in mind, a question naturally comes. Since it is the long diagnosed time that causes the doctors to prescribe broad spectrum antibiotics, is it possible for us to select the right narrow spectrum antibiotic by speeding up the diagnosed time? And the answer is yes. Before I introduce with my method and solution, here's a quick introduction to this technology called microfluidics. Now, this is basically a fluid control technology at a microscale. The way it works is because water and oil, they don't really go together. So when a person forces water and oil to intersect at a point and pushes them forward, you will see a phenomenon of oil phase cutting through water continuously. Therefore, it creates water droplets that is wrapped around in oil. And by applying microfluidics to the incubation process, we're able to significantly decrease the time it takes. And the key lies in the bacterial density. Now, the whole point of culturing and incubating bacterial solution is so that the bacterial density inside the solution to reach above a threshold to be detected as positive. Now, as you can see on the tube on the left, this is a standard tube used in traditional medical testing, and it has a bacterial density of 10 to the 5th CFU. Now, CFU stands for colony-forming units, which is a measuring unit that calculates the amount of bacterial colony there is after culture in a single unit volume. In this case, the unit volume is the tube. Now, after we apply microfluidics to this bacterial solution, we can disperse all of these solution into micro droplets that are around 30 micrometers in diagonal. Now, after we disperse them, we'll end up with two different kinds of droplets. The first kind is droplets that don't have bacteria inside. And the other scenario in which we have droplets with the bacteria. Now, remember what I said about CFU is calculating the amount of bacterial colonies inside a unit volume. After we apply microfluidics, we switch the unit volume from the original test tube as a whole to each individual micro droplets. And since we have all the empty droplets that takes away the extra space and volume, we're able to decrease the volume in each droplet that has the bacteria significantly. Therefore, we're able to increase the bacterial density from 10 to the 5th CFU to 10 to the 8th CFU. And with the higher initial density, we're able to the bacteria is able to cultivate much faster to reach the same threshold. And you may ask, okay, we might have a plausible way to tell, to speed up the process. Then how are we able to tell whether the bacteria is alive or not after it interacts with an antibiotic? So the answer lies in this color dye called resaturin. Now, resaturin is non-fluorescent in itself, but after it interacts with living bacteria, it has this ability to be reduced back to resorphin, which is a substance that has a red fluorescence. And with that in mind, and after applying resaturin to a bacterial sample, we're able just to put it under a microscope and check if there's any indication of fluorescence. And kind of tying all I've previously mentioned up together and make it more automatic, I have designed a chip to realize that. And I've actually brought samples here with me. And I'll first invite the judges to take a few looks at this. Here. The first one. Here's the one for the second row. Oh, this is the more. Yes, this is the one. You guys can check that out later if you would like after the presentation. The chip itself might be a little bit different than what I'm showing right here. This is because the process is due under modification, but the general idea is the same, in which we'll have two different types of inlets, one for the bacterial solution, which is usually urine samples, and the other inlet is for oil. Now, remember what I said earlier about how to create droplets by using oil and water? As you can see here, in the intersection between the two different kinds of inlets, we'll have, this is what we call as a droplet creator, in which this will produce droplets at this micro scale. And then after droplets are created, it will spread through the microchannels into the incubation tank. And after which, we'll also, as you can see on the graph here, we'll have a side inlet that is currently not on the chip itself, but I will definitely consider adding it because it is a prototype. But the idea is that we will have both the resaturin and also the corresponding antibiotic inside the small inlet on the right. And after all the droplets are inside the incubation tank, we can keep extracting air from the other side and using negative pressure to drive all the remaining substance out. And after adding the urine sample and bringing them to the incubation tank, we'll incubate the chip for about 3 to 4 hours at 37 degrees Celsius, which is the normal human body temperature that is most ideal for bacterial growth. And after incubation, we can use the microscope to picture the fluorescent result of the samples. And how did I get the incubation time to be around 3 to 4 hours? So I actually did 4 experiments with 4 different kinds of bacteria to find out the most optimal incubation time. So I compared the incubation time with the signal to noise ratio to determine that how much time it takes for all 4 kinds of bacteria to reach above the threshold line to be detected as positive. And as you can see on the graph, between 3 to 4 hours is when all 4 kinds of bacteria have reached above the threshold. So I have selected 3.5 hours as the most optimal time for the incubation. Now, the graph on the right, the B graph, it's just another indication that how fast the droplet testing is compared to the traditional tubes. As you can see, for all 4 types of bacterial density in terms of CFU, which is on the horizontal axis, the red line, which is the droplet testing, is takes significantly less time compared to the black line, which is the traditional test tube. And what does it look like under a microscope? Now, this is a comparative experiment I did using 2 different kinds of E. coli. One is resistant, one is sensitive to a given type of antibiotic. Now, the resistant bacteria is the first row, and the sensitive bacteria is on the second row. And the 2 columns are a comparison I did between the 2 bacteria before and after I added the antibiotic. And as you can hopefully see from the left column, there are like a lot of visible shining dots on it, and they are indications of bacterial vitality. As we previously mentioned, after we add in resaturin, which will interact with living bacteria to form resorphin that has a red fluorescent light. However, after we add in the antibiotic, as you can see on the right column, only the resistant sample has a few distinguishable lights, whereas for the sensitive bacteria, all you can see is a red background, which is the dead bodies of the E. coli. So by putting the results under a microscope, we can use the fluorescent color to indicate whether a given antibiotic is effective towards a given bacteria. Well, with this technology and a chip, we're able to significantly decrease the volume inside of a testing unit. Therefore, we can dramatically decrease the time it takes for the bacteria to be cultured to a density to be detected. And also, by applying resaturin as our color indicator and dye, we're able to use the fluorescent results that's put under a microscope to tell us about the antibiotic's effectiveness towards a given type of bacteria. Also, by running multiple simultaneous testing of different antibiotics with the same type of bacteria, we're able to quickly determine which type of antibiotic is the most effective towards a given bacteria that infects the patient. And in terms of real-world applications, as I previously mentioned about all the troubles brought by primary and secondary infections of bacteria and the creation of antibiotic-resistant bacteria, with this faster diagnosis time, this will avoid the prescription of broad-spectrum antibiotics from doctors, therefore decreases the patient's risk of developing antibiotic-resistant bacteria. Also, by applying this chip, we're able to decrease secondary infections and shortens the medical periods of patients, and further puts the patients away from potential risks. Last but not least, this simple procedure is compared to the complicated and expensive procedures and machines in hospitals, is very much accessible to patients themselves. So they can literally kind of just run the test themselves at home with relatively lower costs compared to the diagnosis that they have to do in the hospital. So maybe next time when you happen to bump into a bacterial infection and you're deciding to go to the hospital, maybe consider buying my chip, because not only it is less expensive, it is much faster and it has the same accuracy. All right, and that's all. Thank you.
Hey, Kevin. I just have a conceptual question about, you mentioned again the antibiotic resistance developed in these bacteria.
Yep.
I was wondering, when you kind of prescribe these like broad spectrum antibiotics, as you say, doctors do it because it's faster at the moment and it's more efficient for the cause. But wouldn't you say that the antibiotic kind of resistance they develop is only targeted for these broad spectrum antibiotics and not for the like the actual antibiotic that they need?
Yeah, so like the idea is that because you're right on the first part in saying that because of the amount of time it takes for current detection methods, doctors would tend to prescribe with broad spectrum antibiotics. And as shown on this graph, the broad spectrum, even though it is more powerful by it targets a variety of bacteria, it also causes a series of problems, such as when it enters the human body, because it targets more bacteria than you actually need, it will also accidentally kill other types of bacteria inside your body that may be beneficial to you, like the original bacterial flora in your body. So that is one side effect it has, because in general terms, like no matter what types of bacteria antibiotic you apply to it, there's a chance of having resistant bacteria that remains in your body due to mutations and stuff. But if you apply the broad spectrum one, that also creates dysbiosis, which is the imbalance between bacteria inside your body, then the resistant bacteria that survive the first round purge will be able to develop much faster than before because there's like this lack of competition with other bacteria. And that's like the main reason that this will lead to the development of antibiotic resistance. Does that answer your question?
Kevin, I have a question.
Yeah.
Actually, I probably know more about this than me, and I feel like I'm going to embarrass myself in front of my biology colleagues here. But sometimes when we get sick, we don't immediately know whether it's a viral or bacterial infection, right? Mm-hmm. Is your design able to sort of help to quickly answer that question? Because my understanding is that that's not something that sort of is quickly answerable. Mm-hmm. When you go and visit the doctor.
Right, that's a great question, and it's something that I was considering, but I didn't have the time to kind of actually put that into experiment. But from what I'm like picturing with this available data and the chip, because viral and bacterial infections are different in the sense that bacterial infections can be treated with antibiotics and virus can be treated with vaccines and other types of medications. So if we imagine a case in which you have a viral infection like the flu, and you add your urine samples into the test, and then you add in the whatever antibiotic that's you have available or that comes with the chip, after you wait for like about 3.5 hours, the incubation time, what will the result be? Well, since it is not a bacterial infection, then the antibiotic will probably do nothing to this bacterial sample. And what ends up is that you will see a graph full of shining dots. That the bacteria is all, or the virus is all alive, or in a sense that because, and also, sorry, I take back what I just said. Let's go back to the topic on resaturin, which is the color dye that will interact with living bacteria to form resorphin. Now, because in this case, it is not dealing with a bacterial infection, but a viral detection, it will not be reduced back into resorphin anymore, so it will not yield this fluorescent color. So no matter how you look or what kinds of antibiotic you add into the bacterial solution, it will all be like pure redness. So that kind of tells you, because you remember I said in the end, if we're able to run multiple simultaneous testing based on different antibiotics, we're able to have more comprehensive understanding of the result. And if we do that and we see that all of the results are like have no indication of any fluorescent light, then this probably means that we're not dealing with a bacterial infection, but a viral one.
Where can we purchase this microchip?
Well, it is still in the development process because there's some modifications, and you guys asked some great questions that I have to consider. But hopefully in the near future, because obviously it is not entirely homemade, that I had the opportunity to work in a lab in Guangzhou that kind of provided me with the original materials. So my current expectation is that once we find a way to, because currently the chip is handmade, right? It's made of PDMS, which is a type of polymer. But if we find a way to transform this production into a factory chain that can be massively produced with the raw material being plastic, then that's the time where I think this chip will eventually come out to market.
This seems like a pretty perfect solution. So my question is, are there any, why isn't this being used, like, are there any like limitations or problems that are causing it to not be
Yes,
like,
I guess.
mainstream?
Yeah, I guess the first limitation is, like I said, the fact that if we are actually going to apply it to clinical uses, then the chip itself has to be like massively manufactured from factories where they have standard manufacturers, because currently it's made of like artificially, so we can't really have a uniform standard or a guarantee of the product accuracy in terms of the construction of the microchannels. So that's the first issue we have to solve. And also is like there's a deficiency in the sensitivity testing, because currently we can only use bacterial solution that's cultivated from like traditional method and the urine sample. But we are hoping to incorporate other like kinds of samples, like blood samples, for example. That will make it more versatile in the future uses.